review of last lecture, we did non-circular flows, so non-circular internal flows. So that's all about hydraulic diameter. And then from there, we can look up our friction factor in table 8-1 from the course textbook. There's 3 types of internal flow problems in increasingly complicated order. But you have examples of all of these between the lecture notes, the problem sets, and the tutorials. So we're starting the last module of the course, and that's on integral conservation laws. So you can think of the reason that that says integral, don't be afraid, it's okay, is because previously in the course when we talked about, say, a differential fluid element, that's considered differential fluid analysis. So we consider differential forces and balances on a fluid parcel, and you can derive F equals ma from that. You can also do that same sort of analysis using integrals. So integrals over control volumes. That's roughly what we're going to be doing here in terms of momentum balance, mass balance. And the last topic in this course is Reynolds transport theorem. That's the same Reynolds that did the Reynolds number. Reynolds transport theorem is a generalized conservation law. So you've heard about conservation of mass, momentum, energy many times by now in your degree. The Reynolds transport theorem is a generalization of all these, so we can come up with some sort of integral equation that describes how anything is transported that we would want to describe. Learning objectives for today. I'm going to try and get through as much of this as possible, but I did think it was important that we kind of do some experiential learning. But we're going to define what a control volume is for a fluid, compare and contrast between balance and conservation laws, calculate some integrals, so mass accumulation and mass flux for a control volume, and we're going to apply this integral conservation of mass to analyze flows. Okay, so I'll get to our notes now. So control volume. So control volume, you guys have seen this before, but just so we're all on the same, I'm assuming you've seen this before, saying heat transfer class, things like that. Is that true? Yeah. You guys are probably tired of hearing about control volumes, to be honest. So it's a closed region in space. It's a volume, control volume. So it's a volume, but it's enclosed by control surfaces. So a volume is enclosed by surfaces, and those surfaces are where most of the analysis is going to happen in this class. Control volumes in general, they can be stationary, moving, rotating, deforming, etc. So control volume is, there's no right or wrong control volume usually. There's just varying levels of convenience of control volumes that we can use in a problem. So a control volume is something that's in our head when we think about a problem. It's not a real thing. It's an imaginary thing. I'm going to draw one now. Say a box control volume. So our control surfaces, I'm going to do in green here. So the control surfaces are these edges of our box. There's a very important normal vector to define on our control volume here. So n hat is going to be defined as the surface normal vector, and it's always normal. It is a unit normal vector everywhere on all the control surfaces. No matter where you go on your control volume, that n hat will always point outwards from the surface. Again, the green here is the control surface. So n hat outward unit normal vector. So n hat is not a coordinate system defining, it's just a vector that our surface is characterized by n hat. Okay. Any questions? I'm assuming most of this isn't new, but Maybe some of the integrals we're going to do might be a little bit new. Let's talk about what balance laws are. So a balance law says that the rate of change of something, and that something is just going to be a green kind of squiggly. So the rate of change of something is the influx, whatever that balance law is for, minus the outflux plus generation minus consumption. So kind of in words, this is the left-hand side of this is called the storage or accumulation. So if we have a control volume, the amount of green in our control volume, if it's going up, that means we're storing. Um, if it's going down, that means we're kind of getting rid of. So it's going outwards through our control surfaces. The influx minus outflux, we can think of that as like a net flux. This generation, consumption, you can think of that as a source or a sink. So source and sink terms. So that's a balance law. There are many things that are governed by balance laws, but a more strict type of law is a conservation law. The thing that characterizes something that's conserved rather than something that's just balanced is that there's no generation or consumption allowed. So can anyone think of some examples of things that we're not allowed to generate or consume? Yes, Aaron. Entropy. Okay. Yep. Sorry. Engine coolant. You're not okay. Well, you're not allowed to generate or consume that, but your car might be if it's not running too well. Anything else? Something much simpler. What's something that's governed by a conservation law? Yeah, mass. Mass. Yeah, that's what you should say. So matter. So we're not allowed to generate or consume matter. So what the law looks like is d by dt of that thing is the influx minus the outflux. So there's nowhere for this thing that's conserved to go. Once it enters our control volume, it either stays in our control volume or it leaves our control volume. That sounds simple, but you have to think there's no way that this could be generated or consumed. It can't just vanish. So that thing is therefore governed by a conservation law. So for example, mass, momentum, and energy. So since we only have the left-hand side of this, storage and accumulation, and the right-hand side, flux, which you can think of as kind of the net flow, we only really have two physical processes to deal with in fluids. We only have storage or accumulation and flow. So the right-hand side of our conservation law is flow. The left-hand side is storage or accumulation. So under what I have a question for you guys. So under what condition would the storage or accumulation be 0? You have your hand up? Okay, yeah. Steady state. So if we have a steady state condition, there's a couple ways you can think about that, but the d by dt will be 0 for something that's in steady state. So therefore our influx equals outflux. So we're not accumulating anything. Whatever goes into our control volume, whatever shape it is, it has to go out the control volume at some point, or else we will store or accumulate, causing some sort of time rate of change. So very good. So accumulation equals 0. For steady state. So this lecture is about mass conservation, so let's focus on mass. So that means our green thing in the above is equal to mass. So the mass in our CV, mass is density times volume. So assume we have some CV that encompasses a region of space. The mass is just equal to density times volume. So there's an important assumption about this, and that's that these are both constant. So in general, we can't assume that. Because this constant volume assumption is kind of, if your control volume is moving in space, you have to account for that when you're doing your conservation of mass, right? So if your volume is itself of your control volume is changing, this won't be true. So what we need to do is do a volume integral of density in order to get mass. So that's, say, for a changing rho. This is the mass at a given instant. So if we're talking about the time rate of change of mass, because remember in our conservation law, we're trying to conserve mass. So we're talking about the time rate of change. We need to take d by dt of this. So dm by dt is just v by dt of the above volume integral. So now if our imaginary control volume is changing in space, and we know kind of how the density varies in space, we can calculate how the mass changes in time. Okay, so that's, remember, as we just discussed, this integral is 0 for steady state. Again, the green part there is not always the case. So are there any questions about this? So I know I've probably lost a bunch of you that I've put a triple integral up there. Don't worry too much. It's not a Calc 3 course or anything like that. This integral, remember in this class we deal with incompressible flows. So that means what about the density? Anyone? Yep.
It's not changing.
It's not changing, it's constant. So the density doesn't change in space or time. So the density will come right out. So Usually, I'm not going to say you're not going to be asked to do a triple integral in this class, but I won't ask you that on purpose. So we're not going to do triple integrals. You're going to see how this analysis ends up working out. This is more of an idea. So we have some sort of density in space, a volume in space. This is the truest representation of that mass. But we're not trying to test your triple integration skills in this class. We're trying to test your conservation law skills. Okay? So don't worry too much. I hope I've brought some of you back from the triple integral glaze in your eyes. Okay. Unfortunately, we're about to see a double integral, so it might come back. Okay. So this was our first physical process. This was the accumulation. So the rate of change of mass is accumulation. Right? dm by dt is our right-hand side of our conservation law. That is accumulation. What was the second physical process I say? We only had two, right? Flow, right? We can only accumulate things or we can move things. So because we can't create or destroy mass. Okay, so we have flow now. So remember from internal flow, mass flow rate, m dot is rho v average A. So let's have some sort of control volume here. And take a very small element. So I'm just going to zoom in on this kind of element here. Okay, so how do we determine the flow through this very small element? So we need to do basically rho times v times a of this small element. But there are some special things we have to account for. In general, the reason that internal flow it was just rho va was our area was always perpendicular to our flow, right? If you have flow in a pipe, you take the cross-sectional area of the pipe, the flow is always like this. That's not the general case. So we could have flow coming in at like an oblique angle here. So the green is the velocity vector v. Sorry, did I say green? The blue is the velocity vector v. And it's coming in non-normal to this area. So say our area is like this, the velocity is like this. So the only way that flow can go into our CV is through the normal component of the velocity vector, right? So how do we get the normal component of the velocity vector? Any ideas? Projection, right, onto the normal vector. So our normal vector, I said, we always have wherever we are on our CV, it's defined by this normal vector. So our small area has this normal vector, and that tells us exactly the normal direction of the surface by definition. We're also going to call the area of this element dA. So the m dot there is going to be rho the velocity vector dotted with our normal vector times the area. This is just rho v normal times A. And again, the reason for this dot product is that the velocity that convex, so convex is a fluid's word for kind of moves. So the velocity that convex our mass through dA is the normal component. So we're going to see this v dot n a lot. So are there any questions about v dotted with n? Again, we're not changing the magnitude of, say, this normal component with the velocity because n is a unit normal vector. So when you have a unit normal vector, you're just basically doing a projection. You're not changing the actual velocity magnitude. So any questions about this v dot n concept? It will show up quite a bit. Now there's an interesting thing to note about the v dot n. Let's say we have flow through a pipe or flow between two walls or something. So we'll take our CV boundary as the pipe walls. So inside here is our CV. So say flow is coming in like this. Our normal vector always points outward. It's the outward pointing unit normal vector. So that means, again, this is the in, this is the out. So v dot n is that going to be positive or negative? Any guesses? Just take a guess. You're 50-50. Negative? Okay. I'm hearing some not very confident negatives. You're right. It's negative because the vectors are in opposite direction. So v dot n is less than 0. What about on our right-hand side? So where flow is leaving our CV. What is v dot n there? Positive. Okay. It's positive. So this is kind of an interesting problem, I guess. It's a problem because we would like it if our CV is accumulating something. That means that the inflow is greater than the outflow. So accumulation should be like a positive time rate of change. But our mass flow rate, the way we've defined it here, is actually negative. So inflow is negative. Which is weird. So we're going to see a negative sign appear in our equation later. And that's for this reason. It's about when we define our normal vector outwards, we have to account for that sign change. So we can calculate now a very small mass flow rate over our control surface. In order to calculate the total mass flow over all the control surfaces, we have to sum over infinitely many small areas, which is what a double integral is, an area integral. So this would give us, here, let me do this. So the area integral of rho v dot n dA. I just took that small mass flow rate from up there, rho v dot n dA, and I put it in an area integral, meaning I'm going to do that integration over all the surfaces. And in the cases that we'll analyze, this is going to be much simpler than doing a double integral. So the way I've defined this, if I do this summation, when this is positive, it's an outflow. So this integral actually gives me the net flow out of the CV. But conservation of mass says that the accumulation of mass should be directly equal to the net flow in. So that's why we're going to have a negative here. So if I do a negative rho v dot n, That gives us our net flow in. So our conservation law, now we've basically come up with an integral expression for both physical processes, accumulation and flow. So our conservation law just says that the accumulation is equal to the net flow. So we can set these two terms equal to each other. d by dt of our volume integral is equal to the flow. So this is just accumulation is equal to the net flow. This is basically the integral form. Again, the physical variable that's conserved that we're talking about is mass. So this is basically the integral form of conservation of mass. Are there any questions? I know it's very abstract right now, but promise for the rest of it, it will be very concrete. Any questions? Okay, so we're gonna do some, let's see. I'll cover the example that I have on Friday's lecture, but we can do some Menti kind of understanding of these concepts now. So you can pull your Menti back up. So on the right here, I have a picture kind of a truck watering some sort of field. So if we take the tank in the back of this truck as our control volume, do you think that our accumulation will be positive or negative? So again, the tank, the CV is kind of this imaginary thing we have that's the exact boundaries of this tank. Okay. So we're a little bit split. Is there anyone who said it was negative that wants to explain why they think it's negative? Because it's losing volume, right? So you would expect the accumulation to be negative because if it's accumulating and it's positive, it should actually just be accumulating volume. So if you're losing volume, it'd be negative. So it is negative. Um, Maybe did that explanation help some of the people who put positive, or are there any questions about why it's not positive? So our tank is our control volume. So we're sort of anti-accumulating volume. We're throwing away volume. So that's going to be a negative accumulation, right? Any questions on that? So we would expect when we do this volume integral, we would expect a negative result. So now what about the other term in our conservation law? So the flux or the flow. Again, remember, this includes the negative. This includes the negative. So this area integral would encompass the boundaries of the CV, and the flux through those CV boundaries, the only flux you would get is where it kind of leaves the tank to go to this front hose and where it leaves the tank to go to the back hose. So that's the only thing that you really have to consider in that area integral because the flow out of the other sides of the tank is zero. So maybe does someone who said this term was positive want to say why? The flux, uh, remember this is the negative sign in front of that flux is the flux in to our tank. So someone want to explain their answer? Okay, because the answer is negative. So Remember, the conservation of mass is just that accumulation is equal to the flux in. So when I put the negative sign in front of this integral, that's when we get the flux in. So we're actually not getting a flux into our CV at all. We're getting a flux out of our CV. So this whole thing would be negative. Any questions there? It's basically, you would, yeah, so this term would be positive. We only have flow, we only have flow leaving our control volume, right? So wherever we do this integral, our velocity will be aligned with our normal vector. So this integral without the negative will be positive everywhere. We put the negative in front and then that whole thing becomes negative. Okay, let's try a different. So let's assume we take this whole field as our control volume. So we forget that there's a truck on top of the field. Other than remembering that it's spraying water onto the field, let's consider this field as a control volume. And what do we think the accumulation term would do there? So I think this one's a little bit more simpler. The field is going to accumulate water, so you expect it to be positive. The field's not losing water, it's gaining water, so we expect a positive accumulation. Now let's see how we have kind of adjusted our answers from last time on the flux. So what about the total flux in to the field? So the field, I guess, if we assume the field isn't losing water some other way, the only sign we get when we do our, I'm going to draw it on the board. So if the field is kind of the ground, the field is our CV. I picked the wrong marker apparently. Let's say the field is our, let's say this line here is the field. Our normal vector is always pointed upwards, and the water spraying, the velocity is always going to be downwards. So that v dot n will be negative. That's part of the integral is negative. And then we multiply it with a negative for the reason that I mentioned, that we want basically a flux in to be positive. So I think more people got it right this time, definitely. What about this example? So assume we have a distillation column. You consider sort of the bounds of that distillation column as your control volume. What about the accumulation term there? In a steady state flow case, which if you have a distillation column at home, you probably want to run it under a steady state flow case most of the time, or else it will fill up and become quite dangerous. Or I guess it could drain. Okay, so it's equal to 0. So we don't want to accumulate anything over time. So what does that mean about our flux? Because we have flux, you might have flux in and out of this. But if we're not accumulating at all, what do we say about our net flux? Yep. Yeah, exactly. So there are a bunch of integrals, but they're really saying simple things. It's just that you have a net zero flow rate. So your integrals over all these little pipes connected into your distillation column, they have to all add up to 0 in order to not get a net accumulation of fluid. So let's say here, what is the sign of that flux term? So the previous term, the accumulation term, it was 0, say, just because d by dt of something that's steady is always 0. But this is more of a nuanced integration because you have several non-zero parts of this flux, right? You have flow coming in and out of your column, but that all has to add up to be 0 for steady state. So this is the sort of thing you have to wrap your head around for this conservation law thing. So it is equal to 0. So it looks like most of you got that. This is what we have to wrap our head around for conservation because we're doing mass today, but we're going to extend this to, say, momentum. And momentum becomes more complicated because the momentum balance and momentum flux isn't just one equation where basically accumulation equals the net flux. It's a vector equation. So it's going to just get a little bit more complicated from here. Are there any questions or anything particularly confusing that I can clarify about this? Yep.
This question is probably terrible at extending vector calculus, but how come we just don't define the normal vector into our
It's a good question. Yeah, it's not related to understanding of vector calculus or anything like that at all. So the question was just why do we define the normal vector that weird way, always pointing out? It's just pure convention. So the entire thing in the field would just be reversed if you define the normal vector pointing inwards.
It's like conventional current. It's like
Yeah, just convention. So the normal vector always points out. So everyone's always using the same normal vector. Yeah.
but it's not wrong to do it that way.
Don't do it the other way. If you do it the other way, you will technically get the right answer. But all the equations that I will be given will be based on the field convention, which is that the normal surface normal vectors always point outward of a surface. That's just a geometry convention, okay? I didn't just make that up, trust me. Any other questions?